Let's start on lecture 19, interrupts. Just a reminder, the homework is due on June the 12th. In today's lecture, we're going to talk about several concepts. We start with exceptions. Exception refers to an unexpected event alerting normal program flow. It's often the result of an error. It can occur in hardware or software. For hardware exceptions, it's often handled by the operating system. And it'll trigger the stop of a running program. For example, if you encounter a division operation and the division is by 0, or if you encounter system reset, or for protected mode operations, if there's an invalid access to a protected space or breakpoint, these will generate exceptions. Some programming languages, for example Java, C++, and C#, have software exceptions for program-related events. For example, in Java and C++, you can have so-called try and catch blocks. You can attempt certain code, and if that code fails, then the catch statement will cause an exception. Exceptions are typically synchronous events. That means exceptions, what we refer to here, occur in the course of executing a single instruction. Second concept is the interrupt. Interrupt is a CPU signal that external event has occurred. Interrupt or interrupt signals are often generated by external hardware. It's to signal the processor to interact with peripheral devices. For example, when you press a key on the keyboard, or when a printer tries to read from memory, or a timer completes its counting, it'll generate an interrupt. It can also be generated by specific instructions on x86 architecture, for example, using INT, INTO, or bound instructions. Interrupts are sometimes seen as subsets of exceptions. One major difference between interrupts and exceptions is that interrupts typically are asynchronous events. Because hardware signals can be generated at any time, that's solely depend on the peripheral device. For example, you can press the keyboard at any time of the execution of the program. The current instruction will be completed before an interrupt is handled. This diagram shows a typical interrupt timeline. We have 3 interrupts happen along time axis. First is a keyboard interrupt. This keyboard interrupt will momentarily interrupt the main program, and after its interrupt service routine completes handling the keyboard input, the main program will resume. So that's why you see this shadow here. This is what the microprocessor has to do to handle this interrupt from keyboard. This part of the code is different from the main program. Similarly, at some point, there's an interrupt comes in from printer. Maybe because printer tries to read data from memory. So this interrupt will cause the main program to pause, and a special code, which we call interrupt service routine, or ISR, will be executed to handle the interrupts. And these interrupt service routines are very device specific or interrupt specific. For different interrupts, there will be different operations necessary to handle. And these interrupts can occur at any given time while the main program is being executed. in this diagram, you can see that both of these two interrupts happen the second time. Inside an interrupt service routine, these are the things are commonly done. The interrupt service routine has to decide whether or not to serve. Oftentimes, it has to stop the main program to serve the request or to provide necessary data to the peripheral device. But the steps for doing so are processor dependent. If it is decided that the interrupt service routine has to provide response to the hardware, it will complete the current instruction. It will save the program counter, PC. This is because once the interrupt service routine is completed, the microprocessor needs to know where to return after that. In a sense, the ISR is like a function, but you don't explicitly call this function. The microprocessor also has to save its state, including registers, general purpose registers, index, whatever registers, and also condition codes. It will then jump to the start of the interrupt service routine. That's where the actual operation will begin. And the operation could be acknowledge the interrupt, transfer necessary data between the microprocessor's memory and the peripheral device. At the end, the interrupt service routine will return because we saved the program counter at the beginning, so that's why we can get back to the main program once this ISR is completed. Vectors, or more specifically, interrupt exception vectors. These are the starting address of a service routine. On x86 microprocessor, it composed of both segment and instruction pointer, or CS colon IP. That's how we typically refer to an point in the program segment. And these vectors are typically stored in a vector table. In x86, this table is in low memory range, starts at address 0. There are some vectors dedicated to specific exceptions and interrupts. For example, division by 0, page fault, alignment error. So all these vectors are fixed. This has the benefit for designing operating systems, because if you have these fixed interrupt vectors for any OS, they can design in a uniform way so that if any of these interrupt or exception happens, the operating system will be able to get to the correct entry point to handle such events. There are slots in this vector table that can be used by users to define user-specific interrupts. This is just a snapshot of the x86 vector table. It's not very clear here on this slide, but first 32 vectors are reserved, and first 5 are the same for all Intel processors, and there are remaining 224 vectors available for users. x86 also has a number of interrupt instructions. They are used to invoke specific interrupt handlers. For example, int n is an instruction to invoke interrupt with vector number n. For example, int 3 is a 1-byte breakpoint instruction, and this can also be used as a breakpoint interrupt for debugging your programs. INTO is to check for overflow, If OF is 1, it will call the overflow handler or vector number 4. For bound, this instruction is used to compare a register to the boundaries of an array of data. And if the register index is out of the boundary of the array, it will trigger interrupt. Similar to subroutines, at the very end of the service routine, there will be a return instruction. And here, because it's interrupt handler, so we have this IRET. I stands for interrupt. When x86 tries to process the interrupt, it will do the following things. First, flag register's contents are pushed onto the stack, and then it will clear two flags, interrupt flag and trap flag. Interrupt flag, or IF, enables interrupt if IF is 1, and trap flag will cause trap interrupt after each instruction. This is essentially how you do the single steps. So the debug program will set or unset this trap flag alternatively to make sure that you will execute one instruction, then stop, giving you the chance to look at the variables and memory contents before you continue the debugging. CS and IP are pushed onto the stack so that once the service routine is done, the microprocessor can get back to the main program. After that, interrupt vector will be fetched from the table, and this interrupt vector is in fact the new CS and the new IP that will guide the microprocessor to the service routine. They are used to override CS and IP register. Physically, there are pins for the microprocessor to sense these external interrupts. Processors supporting external interrupts have at least one interrupt pin, which can be used to wire with other devices or controllers. A processor can have multiple pins for interrupt purposes, and they often have different level of priority. High priority interrupts can interrupt low priority ones, but not vice versa. Lower priority interrupts are masked out when higher priority interrupt is executing. If only one pin or multiple devices at the same priority, we need a method to determine the specific device causing the interrupt, and then decide whether to respond to it or not. And this discussion here, interrupt pins, are kind of generic to all the processors. And then we're going to look at, for x86, what are the interrupt pins. Intel processors have two interrupt pins, INTR and NMI. INTR is the basic interrupt line. And this pin can be enabled or disabled by the IF flag, the interrupt flag. If IF is 1, this pin is responding to external interrupts. If IF flag in the flags register is set to 0, then this pin is kind of masked out. The other pin for the interrupt is the NMI, or non-maskable interrupt. This pin cannot be disabled by setting or resetting the IF bit. This pin is used for major errors, for example, parity fault from memory chips or power failure from an interrupt power supply. There's a single output from x86. Here the output we're talking about a physical pin. So it's a wire going to be connected to this pin. And the signal on this output pin is for interrupt acknowledge. The INTA pin is to tell the external devices that their interrupts are being handled. So this INTR or NMI, these are the inputs to the microprocessor. So the signals coming into the processor to tell the microprocessor, the x86, that there's something going on. You need to pay attention. You need to entertain. And then this INTA is the output from the microprocessor, from the x86, to tell the external devices that you're fine. Right now, currently handling this interrupt. Just hang there. Device typically respond with vector number. And we talked about vector table. And in vector table, we have multiple entries. In fact, we have 256 entries in the vector table for x86. The device should respond with this vector number to tell the microprocessor what kind of interrupt it will need. Device may have stored state that it needs to clear to avoid requesting multiple interrupts. So this INTA is for that purpose. Once the device sends an interrupt by raising this INTR pin, it will expect to get this INTA from the microprocessor, and once it sees this INTA is asserted, it will stop asserting this INTR. Because if you keep doing the INTR pin, the processor is going to keep responding to the event. So it's kind of a handshaking between the microprocessor and the external device. External circuitry can be used to combine INTR lines to drive IRQ lines to drive INTR. If multiple devices are connected, we need the ability to choose the correct vector. Because for x86, it only has one interrupt pin, well, including the NMI, we have two. But for INTR, we need to be able to figure out of these many devices, which one sends the request. So the hardware solution is that we're going to have a logic to generate correct vector number depending on the device causing the interrupt. We're going to look at a diagram shortly. But let's assume that we have multiple devices that are active and we have separate vectors or priorities for these devices. We can also use programmable interrupt controllers, and the controller will decide which device has higher priority. For the software solution, the interrupt service routine can pull the device to find which one caused the interrupt. So let's look at this scenario here. On the left, we have this microprocessor, and we have interrupt pin, INTR, and we have this INTA, which is active low. That's the acknowledgement coming out of the microprocessor. And we have from 0 to 6, we have 7 devices. And this IRQ0 through IR6, they represent the interrupt signals coming from each of these individual devices. Because these are individual devices, and chances are these could be high at the same time, or could be low at the same time, because this is active low. That means 0 indicating is the interrupt happening. But either way, if one of these is 0, it will cause this NAND gate to output a 1. It's a NAND gate. If any of these input is a 0, that's going to generate a 1 here. And the 1 indicates that this is a moment we have something going on from the devices. Someone is raising the interrupt signal, is requesting services from the microcontroller, from the microprocessor. Now the question is, how do we know which one is generating the interrupt? So we have a octal tri-state buffer driver, the 74ALS244. This is a buffer driver which will send this input to the output side when it sees a 0 from the INTA. Because we have the INTA connected to the control signals here. If the INTA is 0, that's an output from the microprocessor, that is say from my microprocessor x86 is now responding to your interrupt. So this input will be sent out to the output side. So the IR0 to IR6 could be zeros and ones. This byte will be passed onto this output side. And look at what we tie this output to. This is the data bus. This is the data bus of the microprocessor, of the 86. So at this moment, by reading the value on this data bus, the microprocessor will figure out which one is 1, which one is 0, because you have a byte here, and this is passed through this buffer. And from looking at this 0, 1, this bit vector, the microprocessor will be able to figure out which device generated or not generated the interrupt. And out of these 7 devices, it can assign its priority. I can choose to service one of them if I decide, let's say, the priority goes up from IR0 to IR6. I can service IR6 instead of IR5 when both of them are asserted. I'll skip this example.